Construction, working and principle of FTIR spectrometer, Fourier transform infrared spectrometer. Introduction. So let us see what is spectroscopy. Spectroscopy is the study of the interaction of electromagnetic wave with matter, and the instrument that measures a spectrum is known as spectrometer. FTIR spectrometer is an important instrument in the field of spectroscopy. An infrared spectrum consists of a fingerprint of a sample with absorption peaks which correspond to the frequencies of vibrations between the bonds of the atoms making up the material. The IR instrument is of dispersive type. This instrument separates the individual frequencies of energy emitted from the IR source by a prism or grating. The detector measures the amount of energy at each frequency which has passed through the sample. FTIR spectroscopy was developed in order to overcome the limitations encountered with the dispersive instrument, especially the slow scanning process. Construction of FTIR spectrometer. A typical FTIR spectrometer consists of the IR source, interferometer, sample and sample compartment, detector, amplifier and computer. Source. Different types of lamps are used in FTIR with different ranges. For mid-IR radiation, silicon carbide is heated approximately at 1200 Kelvin. Higher temperature source like tungsten halogen lamp is used for near IR range. For far IR, a mercury discharge lamp is used. Sample and sample compartment. The sample preparation is very important for IR spectra analysis, where the sample is placed in the cell or in the holder. The cell is constructed with ionic materials such as KBr or NaCl. The compounds are finely grinded with KBr salt and then pressed at high pressure to form pellets called KBr pellets. In another method called Nugel mold, the compound is finely grounded with the mineral oil called Nugel. As a result, a thick suspension is formed which is placed between the plates. Interferometer, Michelson interferometer is usually used. Detectors and amplifiers. Detectors convert the light energy to electrical energy. Amplifies the signal. Computer. In the computer, fast Fourier transformation takes place. Let us see the working principle. What happens? These are the instruments with which FTIR spectrometer is built up. This is the source. This is the collimator. What happens? Infrared radiation will go to this collimator. The work of a collimator is to direct parallel rays of light to this beam splitter. Okay. From this beam splitter, the beam splitter will send 50% of light to the fixed mirror and another 50% of light to this moving mirror. Then the light ray will get reflected in both the cases. Also from here. Correct. As the mirror is moving, it is directed by a laser. The measurement is taken with the help of a laser which is not shown. The mirror is moving. Obviously, there will be a path difference in each case. If the path difference is an integral multiple of the wavelength, as you know from the Young's double slit experiment, it is a constructive interference. And if it is an odd multiple of wavelength, it is a destructive interference. So we people actually get an interferogram like this. Okay, it's not properly shown. Okay, we'll see it in the next page. So here, then this light will go to the sample compartment, and the IR active substances should have a net dipole moment. This is the most important condition for IR spectrum. Let us go to the next slide. Uh, when the light will go to the sample, it comes out. Uh, Actually, what happens? Several type of vibration occurs between the bonds of the molecules. There are two types of vibration. One vibration is known as stretching vibration, which is again divided into symmetric vibration and asymmetric vibration. And another type of vibration is known as bending vibration, which is divided into twisting, rocking, scissoring, bending, and, and this four. Two of them are out of plane and two of them are in plane. Actually, chemistry people are master in it. We don't need to have a master in this kind of things. So our motive is to learn the physics behind this instrument. So the light will come up. Obviously, some of the rays will be absorbed in this sample based on the vibrations. Suppose if, let me cite an example, the frequency of the light is 5 Hz. Obviously, the ray of light will consist all the frequency that comes from the source due to the interferometer 5 Hz, and if the bond vibrate with 5 Hz, they consider this is actually a resonance phenomenon. Then this light will get absorbed. But if this vibration is 5 Hz, that is the vibration of the bonds of the molecule, but this vibration is 10 Hz, this will not get absorbed in that molecule and it will be transmitted. Okay, I hope the concept is clear to you. So when it will come out of the sample and will go to the detector. In the detector, we have analog to digital converter and we actually get interferogram, digitized interferogram in another word. And this interferogram will go to the fast Fourier transform computer. From this fast Fourier transform computer, we get a spectrum. The y-axis is percentage transmittance and the x-axis is wave number. So this is the physical phenomena, the physics behind FTIR spectrum. Several kind of detectors are there. Pyroelectric detectors are mostly used. Triglycerin sulfate and deteriorated triglycerin sulfate. So let me go to the mathematical part. The mathematical part is saying, yeah, what I have told. Interferogram is actually the intensity versus optical part difference, which is in centimeter. It is Fourier transformed within the computer, and we get intensity versus the wave number graph, which is known as FTIR spectrum. We can use the equations A is equal to log of I naught by I, where I naught is intensity in background spectra, I is the intensity in sample spectra for qualitative analysis. Qualitative means which sample is present, because that spectrum is actually acts as a fingerprint. So it is unique. I will explain this in the next slide. We can use the Beer's law, which is given by A is equal to epsilon LC. You can see their meanings. So we can also do the quantitative analysis. That is how much quantity, what concentration is present. And this is the transmittance formula. So prior to the sample analysis, we take the background spectra for minimizing the carbon dioxide and water contamination peaks. So without the sample, we will allow the passing of the radiation through our experimental setup and then put the sample and take the measurement, and from that we get I, and from the previous one, that is background, we get I naught, and use this formula for finding absorbance and transmittance, and the computer actually plots the graph and we can easily say which sample is present. So let us see the application. It is actually useful for organic analysis like alkanes, alkenes, alkynes, aromatic hydrocarbons, alcohols, phenols, aldehydes, ketones, etc. and so on. So you can see the graph of octane and decane are not same. The peaks of observation, the wave number here, it is wave number, it's so small, I think you are unable to see, it's 3000 written. Even I, yeah, I can take this. You can see here it is 1500, but there is nothing absorbed in 1500. So see, these graphs are all different. They act as fingerprints similar to human beings. They will be obviously different, and we can take the references of this known spectra to find which sample is present in the compound. Okay, so I have cited another examples like benzene, toluene, and so on. Some nanomaterials like titanium oxide, iron and cobalt oxide, zinc oxide, cadmium oxide are also there. You can see they are also unique and we can easily identify what are. So other important applications, it is useful in protein study, biology and medicine, soil analysis, also in environmental studies like measuring gas pollutants, etc. So thank you for listening to this. So thank you.